here we go. So yes, what we're going to do then when it comes to graphing rational functions, again, sketching the graphs, all right, I'm just going to identify some like key pieces of information that we should be able to find as part of our kind of like key parts, as part of our, kind of sketching. So the key parts of a rational functions graph. Okay, now, if you do not recall, we've actually already spoken about the graph of a rational function, I believe, back when we were talking about like parent functions and transformations on those parent functions. Okay, the most basic rational function that we ran across was 1 over x. Okay, now we're going to do ones that are more complicated than this. It's going to be like a polynomial divided by a polynomial. Okay, but for the simplest one, you can still kind of get a general idea about what we're looking at. Okay, remember the graph of this had a vertical asymptote on the y-axis and then a horizontal asymptote on the x-axis. So the resulting graph was something to that effect, right? The general kind of shape there. Okay, so these rational functions, they bring in, like I said, some kind of new things that we haven't really witnessed, at least in this class. Again, Algebra 2, you've seen it before. But like I said, the vertical asymptote, that's something we're going to have to like take into account now, potentially, for our rational functions. And also horizontal asymptotes as well. Okay, but now we've done limits, we can kind of get a better understanding of at least the horizontal asymptote and stuff like that. Okay, so first key piece that I want us to be able to identify, and again, this is just more for my purposes here. All right, it's not like some mathematician decided these are the things you need. It's just This is what I would like you guys to be able to do. So we should also first be able to identify the domain, right? That's review from a previous unit, stuff like that. Remember to identify the domain, right? We look at our domain restrictions. And what are the two main kinds of domain restrictions that we want to look out for? We never want to divide by 0 or take the square root of a negative, yeah, okay? Or square root of a negative. The majority of the time, we're going to be looking for dividing by 0. Okay, that's going to be kind of like the main one. Okay, we won't see a whole lot about taking the square root of a negative. Definitely, bless you, dividing by 0. Okay? All right, so from those domain restrictions, we're going to encounter them in two kind of styles. So those domain restrictions, at least the dividing by 0 kind, are going to either turn out to be vertical asymptotes or they're going to turn out to be holes. Okay? So we're going to take those domain restrictions, the ones that make us divide by 0 at least, and we're going to further classify them, right? So they're classified as domain restrictions. We're going to further classify them as either being a vertical asymptote or a hole. Okay? And they will fall into one of those two categories for our purposes here. Okay? Vertical asymptotes. How are we going to know if that domain restriction is a vertical asymptote? Well, they occur at x values, okay, where we divide by 0. Okay, right. Dividing by 0, we don't want to do that. That makes the function undefined, right? Except when we get 0 over 0, okay, right? So dividing by 0, undefined. So like 3 divided by 0, undefined. But if we get 0 divided by 0, that's no longer undefined, that's indeterminate form, okay? And so we have to do a little bit more work here to analyze that. And in this case, if we happen to have an x value that gives us 0 over 0, that indicates a hole. Okay? So then holes, right, occur where our function is 0 over 0. And again, we'll see some examples of this. We'll see some examples, okay, with this. So we'll go into that more when we get there. Cross that bridge when we get there. All right, other things we should be able to identify. Zeros, okay? Zeros or x-intercepts, if you like. And if we want to identify the x-intercepts or the zeros of any function, how do we do that? What do we do with our function? Colby? Set it equal to 0. Right. Remember, right, a 0 or an x-intercept, that is a point on the x-axis, right? And any point that's on the x-axis will have a y-coordinate of 0. So if we set our function to be equal to 0, well, there we are. We set ourselves up. We just find x values that make us equal 0. Okay. Fifth, I want us to be able to identify any horizontal or slant asymptotes. Okay. And for the horizontal asymptote, we are specifically, well, a horizontal asymptote has to do with end behavior, right? Because your function will approach that horizontal asymptote as you go really far to the left, as you go really far to the right or really far to the left. Okay, as you go really far, in the positive infinity direction, as you go really far in the negative infinity direction, you're going to approach any horizontal asymptote if it happens. All right. So the limit as x approaches infinity then of f of x is what we're going to use to find it. And of course, we really ought to also check the limit as x approaches negative infinity as well, as f of x approaches negative infinity. But for the most part, they will be the same. Okay, there are a few exceptions, and hopefully, I think we should see one of those. Maybe not today, but tomorrow, I think. We'll look at more like normal ones, rational functions, and we'll look at some more abnormal ones tomorrow. And speaking of that, we'll also look at slant asymptotes tomorrow too, so just hold your horses on that one, okay? Number 6, okay, if we need additional points, if you got all that information on your graph, and you're like, this looks like a mess, I'm not sure what to do, then just get some additional points. Pick some x values, plug them in, get their matching y values, plot the points. And then finally, after 6 easy steps, we then graph. Okay? It's as simple as 1, 2, 3, 4, 5, 6, 7. Okay? So, let's try one. F of x is equal to 3x over x minus 1. Okay. So we'll start with a very simple kind of rational function. So let's take a look. Number 1, let's analyze the domain here. Okay. Is it going to be possible here for us to take the square root of a negative or an even-powered root of a negative? No. Okay. Is it going to be possible to divide by 0 here? Yes. Okay. So we do have a denominator, right? So take that if you need to. And obviously, I'm guessing most of you guys can do the mental math at what x value would make us divide by 0. 1, right? Okay. But if you, in case your denominator is more complicated, just take that denominator, set it equal to 0, and then just solve. When x is 1, our denominator will be equal to 0. Okay. So then our domain would look something like this: negative infinity to 1, union 1 to infinity. Right. That's our domain. 2. And then from that domain restriction, we now need to further classify it. So it's already classified as a domain restriction because it makes us undefined. But we're going to further classify it. Either that domain restriction is going to end up being a vertical asymptote, in our case, or it's going to end up being a hole. Okay, or holes, maybe. Okay. And it all has to do with whether this domain restriction makes us undefined right, a number over 0, or if it makes us indeterminate form 0 over 0. So let's take a look, right? If I plug 1 in, I get 3 divided by 0. That is undefined. So then it is a vertical asymptote at x equals 1. And that's the equation for it too, right? Because isn't the equation of a vertical line x equals a number? Right? So that is the equation for the vertical asymptote, x equals 1. All right, questions on any of that? Feeling all right? Review from Algebra 2 is easy. All right. Number 3 then. So that means there's no domain restrictions left over. So can there be any holes? None. Okay, there are none. We have no more domain restrictions left over. Okay, and the holes will show up in your domain calculation there, or analysis. All right, let's move on to zeros. Okay. So zeros, as Colby said, it's when we set our function equal to 0. Okay, but of course a fraction is equal to 0, right? So this is a fraction, right? 3x over x minus 1. A fraction equals 0 when what part of that fraction equals 0? Just the numerator, right? So we'll just set the numerator equal to 0, and so we'll divide both sides by 3. So aha, x equals 0, or the point 0, 0 will be a 0. Okay. That's easy enough. Number 5. Keep on trucking here. Let's find our horizontal asymptotes. Okay, so we'll do the limit as x approaches infinity of 3x over x minus 1. Okay. So, Julia, what would this limit be here?
That would be 1.
So the degree in the top is 1, right? The degree in the bottom is 1, so it's the same degree. So it would be the ratio of the lead coefficients, right? Which is not 1.
Oh, 3 over 1.
3 over 1, exactly right. Yep, we got a 3 in front over the 1 there. So 3. Okay? And then, of course, that's going to be a horizontal asymptote. So as we go really far to the right, 3 is going to be our limit. As we go really far to the left, okay, we'll have 3x over x minus 1. Okay? So same thing here. The degree is 1. But since it's negative infinity, well, it's going to be a negative divided by a negative, so it still is positive 3. Okay, so we're still going to end up being positive there. Even though we're approaching negative infinity, okay, we're going really far to the left, it's a negative infinity, 3 times negative infinity divided by negative infinity, so it'll be a positive overall because you're doing negative divided by negative. And so equation for a horizontal line, y equals 3 there. Y equals 3. Okay? All right, number 6. We'll see if we need additional points. I'm going to just leave myself some space for that. I'm going to go jump then to the graph. Okay, now I'm just going to take all my bits of information here. I need to have a vertical line at x equals 1, a horizontal line at y equals 3, and then zeros at 0. So I think I'm going to kind of like, doesn't look like I have really any like negative stuff I need to graph necessarily. So I'm going to maybe put my x-axis a little bit lower than center. Okay. Because I don't really have any, like my horizontal asymptote is at 3, vertical asymptote is x equals 1. So I'm going to like lower my x-axis a little bit. If you don't like to do that, right, if you don't want to think about that, you just want to make them always, centered and stuff like that, that's your choice. Okay. Bless you. Okay. So just putting some tick marks down here. Again, I'm not going to label them, so that assumes we're counting by ones. X equals 1, vertical asymptote. So I'm going to draw in a little dotted line here. Okay. And I'm going to label it vertical asymptote x equals 1. And then likewise, do a horizontal asymptote here too at y equals 3. So let's see here. Maybe I'll just do it this way for right now. And then go this way too. And I can supply you guys graph paper too if you really like to be neat, for your like homework or something like that as well. I can get you some graph paper I didn't think about asking now, and it's probably too late at this point. But anyway, I do have graph paper if you would like it. Okay. But this is a sketch too, so not too worry about that. Okay, vertical asymptote done. Horizontal asymptote done. We have one more point that we know, and that's our 0. Yep, so it's at 0, 0. So we'll just plot that dot right there. Okay. And so that's our graph, or at least that's what we've already come up with, right? So with this single point right here, all right, and knowing that we have this vertical asymptote here, we can kind of guess that we're going to kind of go down towards that horizontal asymptote and then come up and kind of approach the, go down towards the vertical asymptote, and then we'll come up and approach that horizontal asymptote. Okay. Now, vertical asymptotes, will your graph ever cross? Will a graph ever cross a vertical asymptote? No. Will a graph ever cross a horizontal asymptote? Yes, it is possible. Okay. So I think the idea of an asymptote isn't necessarily so much, and this is again just me making stuff up potentially, but I believe because we call these things both are called asymptotes. One we're allowed to cross, one we're not allowed to cross. I always assumed if it was an asymptote, you should never cross it, right? But I think the idea is because we call these things both asymptotes, the idea is more like our function approaches these things, these kind of like linear, pieces. That's why we call them asymptotes, okay? Because our function approaches that certain value or certain thing, okay? Now, is that all of our graph? Is that it? Maybe, right? We don't know, so we should check. We kind of have our asymptotes here dividing up our graph into 4 sections. We have like this section, we have this section, this section, and this section. Okay? Is it going to be possible for us to have more graph in this section of our coordinate plane? Why not? It wouldn't be a function. Exactly right. We know this thing is a function, right? It says f of x there. It's a function. So if I put some graph up here, I'm going to fail the vertical line test. So that's kind of a clue. If you Mathemagic a piece of graph up here and you already have some down here, you made a mistake, okay? So watch out with that. All right, now, I could have some graph here, though, or I could have some graph here. Either one could be possible. But there is some reasoning we could use here to convince ourselves that we don't have graph in here. Okay? How many zeros did we find? Just one, and we've already plotted it. If I had graph over here, if I had some graph over here, wouldn't I have to cross the x-axis at some point because of the vertical asymptote? And if that's so, then that means I would have another 0 here, which means it's not going to be in this section. It's probably going to be up in this section. All right, but let's pick a point here and convince ourselves that that is so. So I'm going to pick the x value of 2 here. So let's do f of 2. I'm going to do the x value of 2 here. Okay, which gives us 3 times 2 over 2 minus 1. So that's 6 over 1, or just 6. So we have the point 2, 6. So 1, 2, 1, 2, 3, 4, 5, 6. Okay, and sure enough, it is in that section. And so we'll just, again, use that point, kind of fill in the rest. Okay, so there it is. Questions on any of that? Easy peasy. All right, well, let's take a look at one more here then. Alrighty. So we're going to graph this function now. Graph f of x equals x squared minus 3x minus 10 over x squared plus 3x plus 2. And in fact, what I'm going to do here is I'm going to give you guys an opportunity to get a head start on these. So I'll go ahead and label out the pieces of information that we're going to try and find. I'll go ahead and give you a couple minutes here to try and wrestle through this a little bit, see what you can figure out and see what you can't, and then we'll go through it here together. one more minute here. One more minute. Watch your asymptotes. If you're going to wait, you can wait too. We're going to go over this couple seconds here, so if you want to hold on, that's fine too. You can wait, go over. Yeah, if you're ever really like you're stuck at something, okay, try and move on to the next thing or whatever. But if you're really stuck, then just hang on. We're going to go over here in like a few more seconds here, or we can just do it right now, I guess too. That's fine. Okay, so the domain, right? We're looking for domain restrictions here. Okay. Can we potentially divide by 0, for example? Yes. Okay. So we're going to take that denominator, x squared plus 3x plus 2. Okay. Set it equals 0. And of course, in this case, to figure out when we do equals 0, what do we need to do in this case to solve this? Factor, right? Okay. So what does it factor to be? X plus 2, x plus 1. So we do not want to equal then negative 2 or negative 1. So our domain will be negative infinity to negative 2, union negative 2 to negative 1, union negative 1 to infinity. I'm getting to my vertical asymptote section there. Okay, so that's our domain. All right. Don't forget, right, when you have two domain restrictions, that splits your number line up into 3 intervals. Right? 2 domain restrictions, 3 intervals. 1 domain restriction, 2 intervals, right? So, anyway, there it is. Okay. So, any questions on that? Domain restrictions? Okay, no. All right, let's go then to our vertical asymptotes. That means negative 2 and negative 1. Either we're going to classify them as a vertical asymptote or a hole. Okay. So, of these 2 domain restrictions, do any of them make us undefined? That is a number divided by 0. Yes, which one? Okay, negative 1, x equals negative 1. So if you plug negative 1, what this means then, right, is if you plug negative 1 into your function here, in the denominator, well, we know we're going to get 0. Do we get 0 in the numerator? Well, let's just check. Negative 1 squared is positive 1. Minus 3 times negative 1, so it's going to be plus 3. So 1 plus 3 is 4. Minus 10 will give us negative 6. So we're going to have negative 6 divided by 0 there. That's not indeterminate form. That's undefined, right? It's undefined, so that is a vertical asymptote. Try the same thing with the negative 2, though. Okay, we know we get 0 in the denominator with negative 2. Plug in negative 2 up top, though, we get negative 2 squared, which is 4. Minus 3 times negative 2, so that's going to be plus 6. So 4 plus 6, 10. Minus 10, 0. We get 0 over 0. Okay, so x equals negative 2 is not a vertical asymptote. It's going to be a hole. Okay. But of course, with a hole then, a hole is like a point, but it's like a non-point, okay? But just because, even though it's a non-point, right, it's an open circle, we can still figure out a y-coordinate for that non-point, okay? Well, typically, if we have an x-coordinate and we want to find the matching y-coordinate for it, we would plug it back into our function. But we already know that if I plug negative 2 into this function right here, I'm going to get 0 over 0. But what can we do to this function? We already able to, sorry? Factor it. Yeah, the numerator and the denominator here. So let's go ahead and do that. So f of x, if I factor the numerator, it's going to be x minus 5 and x plus 2. The denominator, we already said, right, was x plus 2 times x plus 1. So, while when we plug in negative 2, we get a 0 over 0 indeterminate form, we can use this idea of limits that we did in the past, right? If we did a direct substitution to negative 2 as a limit here, we can see at least what we're approaching. We can cancel out those 2's there, and we'll get x minus 5 over x plus 1, which will then evaluate at x equals negative 2. So we're essentially going to use a limit here in a sense. We're going to find the limit as x approaches negative 2 by doing a direct substitution. Okay, I'm just kind of bypassing writing the limit. You don't need to write it either here if you don't want to, but that's what we're doing. So negative 2 minus 5 will be negative 7. Negative 2 plus 1 will be negative 1, and so we end up with positive 7. So we have the coordinate for the hole as negative 2, 7. Okay, there's a hole there. Okay, questions on that? How we found the hole or anything like that? Is that okay? Yeah. Well, did it again? Okay, this is too quick. So we took our function, factored it, canceled. Okay, which results in an equivalent function, or it's equivalent at all but one point, right? At negative 2, this gives us 0 over 0. At negative 2, this gives us 7. Okay, so the y coordinate for the whole of this is going to be positive 7. Okay, so we're essentially using the idea of a limit here in a sense. Okay, it's basically like a limit. We're going to approach that negative 2, but we're going to do it by doing a direct substitution after factoring and canceling. Okay, any other questions on that whole stuff there? Okay, zeros. Okay, do we have any zeros here? Yes, when x is equal to 5. That's right. Okay, again, if you look back here at the factored version, right, this function will equal 0 when the numerator equals 0. Okay, so x minus 5 times x plus 2. Well, that x plus 2, remember, we don't count that as 0. Why shouldn't we? Well, let me do it this way. Okay, we'll set the numerator equal to 0 because the fraction equals 0 just when the numerator equals 0 there. Okay, we get x equals 5 and x equals negative 2, but why didn't we describe that negative 2 as being a 0 here? It's already a whole. Yep, and it's also, you could also think it's restricted from our domain as well. We can't count that, okay, as a point. So the only 0 we really have here is 5. That value of 2, negative 2, is restricted from our domain, which is why we're allowed to count it as a whole. It's a non-point, okay? Last thing. Okay, horizontal asymptote, limit as x approaches infinity of f of x. Do we have a horizontal asymptote? Idris? Is it 1? I don't know. Is it? What do you guys think? Yeah. It is. It's 1. Yeah, okay. Degree of the top is 2. Degree of the bottom is 2. Ratio of the lead coefficients, 1 over 1, which is 1. Okay. We also technically should be doing the limit as x approaches negative infinity here, but because we're going to be squaring the negative infinity and squaring it here, it's still going to be a positive 1. Okay. There will be, like I said, some exceptions where we do have 2 horizontal asymptotes, but we're not worrying about those today. Okay. We're not going to look at those today. Okay. Whew. Now we have all that information. Let's plot. So vertical asymptote at negative 1. My wobbly y-axis there, but oh well. Okay, horizontal asymptote at y equals 1. Okay. We have a hole at negative 2, 7. So negative 1, 2, and then 1, 2, 3, 4, 5, 6, 7. Open circle there. Okay. Let's do like an open circle, right, for the hole. And a 0 at 5. 1, 2, 3, 4, 5. Okay. And so with that 1, 0 kind of in this like section of our asymptotes and stuff, we can see, okay, well, from here we're going to go up towards that horizontal asymptote, and we'll curve down towards that vertical asymptote. Okay, if you want to find the actual y-intercept there, feel free. Plug in 0. You'll get negative 5. So 1, 2, 3, 4, 5. I should have gone through that point, but oh well, you get the idea there. Okay. And then for the hole, we treat that like it's a point. So again, because it's in this kind of sector, we'll then just kind of connect that, and then again, draw. And don't forget to put arrows there on the end to show that it does keep going. Okay, and then voila. Our sketched graph of our rational function. All right. Questions on anything from that? Nay? All right, so here we go then. I've got your assignment here. I'm going to give you some practice with derivatives, the stuff that we saw at the end of the quiz yesterday. Okay, so that's going to be number 53, 56, and 75. from what we did yesterday at the end of the class. And then page 191, excuse me, numbers 31, 45, and 46. Okay? Remember the definition of the derivative. Limit as h approaches 0 of f of x plus h minus f of x all over h. Okay? Yes. Yes, you may. Okay, and if your friends told you the shortcut already for finding the derivative, please actually write out the limit work and stuff like that. Okay? If your friends didn't tell you the shortcut yet, well, you can ask them and stuff like that, but on a quiz or a test, I'll be expecting you to actually show your work.